Hi, so we're going to do an example now. So the problem is an arrow is released from a bow with an initial velocity of 25 meters per second at an angle of 45 degrees from the horizontal. As long as we know these two conditions, we can determine the time of flight, the horizontal displacement, and the peak height of the arrow. So the solution of any non-horizontally launched projectile motion should begin by first resolving the initial velocity into horizontal and vertical components using certain trig functions. So for the horizontal component, the equation is velocity of the initial in the x direction is equal to the initial velocity times cosine theta. And so we know that the original velocity is 45 degrees, so we plug that in to 25 meters per second is the velocity, and then the angle is 45 degrees. And we get the velocity in the x direction to equal 17.7 meters per second. And then now we have to do the vertical direction, which is the same equation. So velocity in the y direction is equal to the initial velocity in the y direction times sine theta instead of cosine. And that goes back to triangles and theta, which we all learned in geometry. So we plug those, the starting velocity again, and then multiply times sine with the initial angle, and we get the velocity in the y direction is equal to 17.7 meters per second. So you may have noticed that these are the exact same. And that's because we have a 45-degree angle, which is one of those special triangles that make sine and cosine the same thing. So yeah, but the solution continues by declaring the values of the known information in terms of the symbols of the kinematic equations. So we know that the initial velocity in the x direction is 17.7, which is what we just found, and then the acceleration in the x direction, which is this way, is 0 because there is no actual acceleration. Like once we throw and have the initial velocity, there's no other forces pushing it in the horizontal direction. And then in the vertical direction, we found also that it is the same velocity, 17.7 meters per second. But there is an acceleration factor in the down direction because gravity is working. So it is acceleration in the y direction is 9.8 meters per second. And that is a constant that we know because that's just how gravity works. Okay. From the vertical information in the table above that we've already filled out in the second equation, which is this equation here, it becomes obvious that the time of the flight of the projectile can be determined by substituting the known values. We can just plug in what we have already. And this is that constant for gravity. And then t, which is what we're solving for. And then so you just solve the equation. And this is negative because it's gravity, and gravity always pulls in the negative direction. So we found that the time is 3.61 seconds. So the total time of flight for the arrow is this number that we just found. And with the time determined, the information in the table and the horizontal equations can be used to determine the horizontal displacement of the projectile. So we use this equation this time, x equals velocity in the x direction, times t, which is time, which is what we just found, plus 1.5 times acceleration in the x direction times time squared. So with the equation selected, the physics problem once more becomes transformed into an algebra problem. By substitution of known values, the equation takes the form of x equals 17.7 meters per second times 3.6077 seconds, which is what this is, rounded, plus 0.5 times 0 meters per second, because there's no acceleration in the x direction, and we're running out of space here, but that's okay, times 3.6 again, seconds squared. And so we just solve that, and then it equals x equals 63.8 meters, which is the total distance traveled. Okay, so the problem also asked for the height of the projectile at its peak, and this is the same as asking what is the vertical displacement of y of the projectile when it is halfway through its trajectory. So halfway through, the time that we found is at 1.8 seconds. And so we're going to determine the peak height by plugging in t equals 1.8. So we plug it back into the first equation. So here we go. Y equals 17.7 meters per second times 1.8, which is half of the original, plus 0.5, which is just a constant, times negative 9.8, which is gravity, and then times the same time squared. So y equals, if you just solve that, it equals 15.9 meters. So that is the height of the projectile at its peak, and we have solved all three components of the question